Bismillahirrahmanirrahim. Assalamu alaikum. Lecture number 8, unit number 1, complex numbers. This is for the free engineering group F.Sc part 1, first year. In this video lecture, we will discuss question number 9 of exercise 1.2. The question number 9 is if z is equal to 3 plus 2 iota, then verify that part number 1 minus z absolute less than or equal to real part of z less than or equal to absolute of z, and then you need to verify that minus time z absolute less than or equal to imaginary part of z, this im of z mean imaginary part of z, less than or equal to z. Now this complex number is given. This is the question number 9 of exercise 1.2. Before to discuss this question, first of all we will revise the definition of absolute of z. That what is the absolute of z? You know that if I consider z is equal to a plus b iota, if I consider z is equal to a plus b iota, then according to the modulus or magnitude of z, which is denoted by z bar, or the absolute value of z is defined as positive square root of a square plus b square. This positive square root is also called principal square root. This is also called principal square root. So this is the definition of the absolute of z. Now graphically you know that the complex number z is equal to a plus b iota in ordered pair form can be written as ab ordered pair. Now you know that ordered pair is actually represent a point in a plane, and that plane in which the complex number is represented is called z plane or complex plane. So let's say this is a unit on the x-axis, which is the real axis, and b unit on the y-axis, which is imaginary axis. This is x-axis, but for the case of complex plane this is called real axis, and this is imaginary axis, but for the case of complex numbers mean complex plane this is called imaginary axis. So let's say on the x-axis mean on the real axis this distance is a unit and this distance is b unit. So this point has coordinate a comma b. So this ordered pair is actually represent this point, and for this point we have an ordered pair AB which shows the position of this point in this complex plane. Now this is the origin 0 0. So the distance from origin to that point in the plane is called z absolute. So you see that this is z absolute, and this z absolute which represent this distance, you know that distance is always positive. So that's why the z absolute is equal to positive square root of a square plus b square. So this is the definition. Now in this definition you see that there involves a square root. So square root is an increasing function. Square root is always an increasing function. Let's say if I just considering square root function, this is a little bit extra but related to the square root function. Y is equal to f of x, which is equal to square root of x, where x is greater than or equal to 0. So when you plot or when you draw this function in the rectangular coordinate system, so this is the graph. This is the graph of this function. Now if y is equal to f of x is equal to minus square root of x, where x is greater than or equal to 0, this thing we are talking in the real analysis. So that's why I am implying the condition on the x that this is greater than or equal to 0, because in case of the real the negative square root is doesn't define. We already discussed in the theory in the history of the complex numbers. So the graph of this function will become like this. This is the graph of y is equal to f of x is equal to minus square root x, where x is greater than or equal to 0. So from this you clearly see that the ordered pairs which is on the graph of y is equal to f of x, these are the ordered pairs. These are the ordered pairs. So these are the values of the function. These are the values of the function, and these are the values of the function for this one. So you clearly see that these are the positive values and these are the negative values. So these positive values must be greater than these negative values. Negative value. You see, you clearly see that. Okay. Now this is increasing function. This is increasing function. This is increasing function. Increasing function. Strictly increasing, and you see that this is decreasing function. This is decreasing function. So this is just about the square root function. Remember that square root function of this type is always an increasing function. So this is a little bit about the square root. I explain this because you see that in case of the absolute there is a square root of the a square plus b square. So this is just a you can say a little bit about the square root function, which is not included in the first year course, but you see that there is square root, so that's why I explain these things. Inshallah, in chapter number 8 we will properly define the function, and then we will graph the functions of different kinds. So now moving towards the question. Now solution, part number 1. Now you need to given is z is equal to 3 plus 2 iota. You need to verify the requirement for us in this question is minus z absolute is less than or equal to real part of z. This is the real, this is notation for the real part of z is less than or equal to z absolute. This inequality can be split. This inequality can be split in the following form. This inequality can be split, that is minus z absolute is less than or equal to real part of z, and real part of z is less than or equal to z absolute. So you can split the given inequality into these two inequalities. Now for z is equal to 3 plus 2 iota, we need to check these two results. So for these two results, first of all I need to find out z absolute. So z absolute is equal to positive square root of a square plus b square. Here a is equal to 3 and b is equal to 2. When you compare z plus 3 iota with a plus b iota, so you will get a equal to 3, b equal to 2. So this implies that z absolute is equal to 3 square plus 2 square square root, positive square root, principal square root. So this implies that z absolute is equal to 9 plus 4 square root. So this implies that z absolute is equal to positive square root of 13. So this is the value of z absolute. Now the real part of z is equal to 3. When you know that when z is equal to a plus b iota, so the real part of z is equal to a and the imaginary part of z is equal to b. So now if this is a complex number, if this is a complex number, z is equal to 3 plus 2 iota, so the real part is 3. So this is RE of z. So you clearly see that. Now and here you can write minus time absolute z is minus square root of 13. So you clearly see that minus square root of 13. Square root of 13, remember that it is greater than 3. It is greater than 3. this value is greater than 3. When you take the square root of 13 on a calculator, you will get greater than 3 value. So you clearly see that this minus z absolute is less than or equal to r of z, because minus square root of 13 is less than 3, and this and r of z is less than absolute of z, because 3 is less than or equal to square root of 13. So combine these two results. So when I combine these two, so I will get z absolute is less than or equal to real part of z, which is less than or equal to absolute of z. That is minus square root of 13 is less than or equal to 3, 3 is less than or equal to positive square root of 13. So this is the required proof. This is the part number 1. Now we will check part number 2. So part number 2 is this is part number 2, minus z absolute less than or equal to imaginary part of z less than or equal to z. So this inequality can also be split into two inequalities, that is minus z absolute is less than or equal to imaginary part of z and imaginary part of z is equal to absolute z. Now I already explained this point that f z is equal to a plus b iota, then imaginary part of z is equal to b. So here the complex number z is equal to 3 plus 2 iota is given. So this implies that imaginary part of z will be equal to 2, and we find in the previous part that z absolute is equal to square root of 13. So you clearly see that this implies that minus z absolute minus absolute of z will be equal to minus 13 square root. So you clearly see that minus absolute of z is less than or equal to imaginary part of z, that is minus square root of 13 is less than or equal to 2, and imaginary part of z is less than or equal to absolute of z. So that is 2 is less than or equal to positive square root of 13. So now combine these two. So when I combine these two, so this implies that minus z absolute is less than or equal to imaginary part of z less than or equal to absolute of z. That is minus square root of 13 is less than or equal to 2 less than or equal to positive square root of 13. So you see that this is true. Whenever you can find out the square root of 13, that must be greater than 2. So when multiply with minus with that value, so that will become less than 2. So this is the required proof, and this is the end of exercise. This is the end of exercise 1.2. Inshallah, in next video we will discuss the theory for exercise 1.3. Thank you.